Hello everyone, welcome to another edition of HL Chemistry Flip Classroom. Here we're going to discuss the periodic table, get you familiar with some of the basic terms of it. Because, ladies and gentlemen, the periodic table is your best friend in this class. You need to learn to love it and to cherish with it. Perhaps you should sleep with one under your pillow. I don't know, but if you get to know the periodic table and use it to its fullest, you can find a lot of success in this class. There's a ton of things we can tell by studying the periodic table, and we're just going to talk about a few of them today. But it's worthwhile to talk a bit about how the periodic table got started. And this guy right here up there in the corner, a Russian, Dmitry Mendeleev, about 1869, he was given credit for making the first working periodic table, or that had some use to it. Now imagine, ladies and gentlemen, living in a time before the periodic table existed. I believe it's frightening to even think about that, isn't it? But nowadays, fortunately, some of these foreigners came and developed a periodic table for us. But what Dmitry did is he organized elements by increasing atomic mass, and elements with similar properties were grouped together. His sort of big leap, and what he's quite famous for, is he left blanks or empty spots in his periodic table for elements that had not been discovered yet. And not only did he do that, but he said, hey, when we discover this element, I think its density is going to be about this, I think its melting point is going to be about this, and so forth, and was able to actually pretty accurately predict these properties when we found these elements. And he was able to do this because there's some pretty good patterns in the periodic table, and again, we can tell quite a bit by looking at it. Now, Mendeleev was kind of an intense guy, didn't really believe a ton in personal hygiene. Here's another picture of him. Just soak that in, ladies and gentlemen. He was quite an intense guy, but a smart guy, and one of the all-time great chemists, to be sure. So, if you looked at Dmitry's periodic table, you would find it looked quite a bit different than the one that you're used to. The one that's more like what we use was developed by Henry Moseley. This was around 1813. He was a British guy. He organized elements by increasing atomic number, which is the way the modern periodic table. There's Moseley, a nice young fellow. Now, sad thing about this guy, if you know anything about your world history, right around 1913, he ended up heading off to World War I and was killed. And he may have done many other great things in science, we'll never know. He also may very well have won the Nobel Prize, but you cannot win the Nobel Prize after you've passed away. They only award it to living people. So poor Henry Moseley cut a tough break there. So we need to be able to look at the periodic table and get a handle on what type of elements that we're dealing with. I would say the most important is the metal versus non-metal. Most of the left side of the periodic table, in fact most of the elements, the majority of them, are considered to be metals. Characteristics of metals: metals are malleable and ductile. Malleable means you can shape them. Ductile means specifically making things into wire. So all metals, to one degree or another, are malleable. Some of them are really malleable. Sodium, which you may not think of as a metal, if you were to touch it, it's dangerous. You probably wouldn't want to touch it, but it's soft enough like clay that you could shape it with your hands. Other metals are obviously not quite as malleable as that, but all of them, once you heat them up at least, you can work with them. The opposite of malleable is brittle, by the way. Clay is malleable, a clay pot is not. So malleable, brittle are antonyms. Metals also conduct electricity. We're going to be talking about that and why that's the case, but that's a pretty familiar property of metals. Another thing is that metals form positive ions, cations. Cation is a term that means positive ion. Now, how are you going to remember that? Well, I don't know. If you like cats, if you are positive about cats, maybe that's one way you can remember that cations are positive ions. I don't know. come up with whatever works best for you as a way to remember that, but that's definitely a term that you're going to see for positive ion. Nonmetals are, for the most part, in the upper right of the periodic table, the upper right corner. Most of these are gases. Some of them are brittle solids, so non-malleable solids, like sulfur, for instance. Nonmetals have low electrical conductivity, and they tend to form negative ions, which are called anions. Now, how I remember this is I tend to think of this word as sort of a contraction for a negative ion. That's how I remember that anions are negative and cations are positive. Now, I don't think that's really where the word comes from, but that's how I like to think of it. Anions is sort of standing for a negative ion. And then I remember anions are negative, therefore cations are positive. I'm not really a cat person, so I don't use the positive cat thing, but it's up to you. Now, right in between where the metals and the nonmetals are, there's things called metalloids. Every once in a while you'll hear them referred to as semimetals, and they're in between on the periodic table where the metals and nonmetals are. And it may not surprise you to learn that they have properties that are sort of in between metals and nonmetals. Probably the most famous one is silicon. Silicon is used in computer chips, and its ability to be a semiconductor is the whole thing that allows it to be able to be used in the process of making computer chips. So its conductivity, silicon's conductivity, is sort of in between that of what we would expect from a metal and what we would expect from a nonmetal. Now, don't get the element silicon confused with silicone, which is different. Silicone is a compound that's used in a variety of things, and there's a bunch of different types of it, but silicon, silicone, not the same. Some other important periodic table terms, and by the way, we're going to look at a periodic table here in a second and make sure we understand where all these are coming from, are periods, which are the horizontal rows, horizontal like the horizon, like this way, that's horizontal. Group or family. Families are the columns. Columns go this way, up and down. Horizontal, horizon, this way. Vertical columns, up and down. Those are the families. There's 18 of those. And there's 7 periods. There's some of these families that you should know in particular. They have names. Group 1 is called the alkaline metals, with the exception of hydrogen. Hydrogen's not a metal, but the group 1 is where the alkaline metals are. The D block elements, which is the middle section, those are the transition elements. Halogens are in group 17. The noble gases, famous for being very unreactive, are in group 18. And as we study chemistry, you know, we'll learn a little bit more properties about each one of these things, but I just want to kind of introduce them to you for now. So here's our periodic table. But by the way, if you have a periodic table, you might want to just get it out and make sure you have everything that I'm going to be mentioning here. One thing that we need to do, if we may or may not have done this already in class or talked about it, but it's a good idea to make a kind of a zigzaggy line, and I'll do it as best as I can with this little guy here, about like that. And the point of that zigzaggy line is to separate the metals from the nonmetals. The metals are everything over here except for hydrogen. Hydrogen's kind of an exception, but everything over here except for hydrogen, even these guys down here, all of these are metals. A couple of these right here on the stair step are semi-metals. We don't worry too much about those. And then everything else, these here on the right side of the stair step, are nonmetals. Really, really, really important that at the very least, if you know nothing else about the periodic table, you need to know where the metals and the nonmetals are. Mixing that up is going to cause you all kinds of problems. So make that line there. If the periodic table, whatever one you use, it's nice to have a line there just so you kind of know where everything lies. Like I said, hydrogen exception, it's kind of confusing where to put hydrogen. Sometimes on different periodic tables you'll see it in different spots. Like I've seen it put up here in the middle. I've seen it put over here. Most periodic tables have it right here. That's fine. Just do remember that it is a gas and it is a nonmetal. The groups, those are the columns. This is group 1, this is group 2, this is group 3, and so forth. They're just numbered like that, 1 through 18. The noble gases here are 18. Group 17 here. Here's the halogens, the alkali metals. And then the section here in the middle, this is the D block, like I think we've probably talked about before with atoms, the ones that have D electrons. This is considered the D block here. This is where your transition elements are in that section. So take a second, make sure you quiz yourself, make sure you know where these things are, make sure you know where your metals and nonmetals are. Super important stuff moving forward in chemistry. Another super important thing that will cause you problems down the line if you forget this. There are 7 elements that are what we call diatomic. Now if you break that word down, di meaning 2, so these are elements made up of 2 atoms. There are 7 of them. And to remember the 7, I think of the term Mr. Brinkelhoff. So notice Mr. Brinkelhoff's name here. It's made up of the elemental symbols for those 7 elements spell out this name. So the 7 diatomic elements are bromine, B, that's Br, iodine, that's I, nitrogen, that's N, chlorine, that's Cl, hydrogen, that's H, oxygen, O, fluorine, F, Brinkelhoff. So if you can remember Brinkelhoff, you can remember the 7 diatomic elements. So again, just to clarify, what I'm saying is, take oxygen, for example, the oxygen that's in the air that you breathe. It's not independent oxygen atoms all by their lonesome. Each oxygen atom always has a little buddy. So I'm going to draw a little bond here. There's a reason I'm drawing 2 lines. We'll talk about that later. So there's 2 oxygen atoms instead of 1. And that's the way that oxygen exists as an element. Now keep in mind, this is only true when we are talking about elements, like pure oxygen, pure hydrogen, pure chlorine. Chlorine is not always Cl with a subscript 2 if it's part of a compound. For instance, NaCl, salt, good old table salt. There's only 1 chlorine there. However, if we could get a sample of the element chlorine, pure chlorine, we would see it exists diatomically. We're going to talk a ton about the diatomic elements. You'll hear me bring it up again and again. Another way to kind of remember where they are is they're in an upside down L-shaped type thing right here. And then you just got to remember that hydrogen's in there as well. Basically all of the elements that are gases except for the noble gases are diatomic elements. So that's these ones right here, and that's those. The bromine is a liquid actually, and it's also a diatomic element. But however you get there, just don't forget the diatomic elements. It will cause you to get so many problems incorrect if you forget about them, believe me. I'm sure there'll be some of you, even in the next year of this course, you'll be making mistakes from time to time. You'll forget about the diatomic elements, and it'll cause you to have an error, and I will write a smiley face, and it will hurt my heart that you forgot Mr. Brinkelhoff. Did I say smiley face? I meant frowny face, of course. So if you forget about Mr. Brinkelhoff all the way up through year 2, expect a frowny face, and I'll be real sad. So don't be that guy. Don't be that girl. Don't forget about Mr. Brinkelhoff. Moving on then, some terms on the periodic table related that we're going to be talking about a fair bit. Atomic radius. So this is, if I had a sample of an element, this is how far apart the nuclei of those atoms would be. That's kind of a more technical definition. It's really okay in your mind to think about this as atomic size. How large an atom is. You know, if you think of the atom as sort of a sphere, its radius, the larger the radius, of course, the bigger the atom would be. So that's a good way to think about it. Something you should not mix atomic radius up with is ionic radius. Remember the distinction between atoms and ions. Atoms are uncharged by definition. Ions have a charge. So we can also talk about ions. How far apart are ions? And we can think about this as ion size, but let's not make sure we understand the distinction between the two. Here we're talking about things that aren't charged. Here we're talking about things that are charged. And all of these things I'm talking about now, we're going to talk about more and really develop these ideas more. Just trying to give you a little introduction at this point, like I said. Electronegativity. When an atom forms a bond with another atom, with another type of element, it might have a certain tendency to attract electrons to itself in a covalent bond. We're going to be talking more about the bonding types in the next unit, but you can sort of think of electronegativity as a tendency to attract electrons to itself. Some atoms have a very strong ability to attract electrons to themselves. Some have a lesser ability to attract electrons to themselves. And that's what electronegativity tells us. A really important trend on the periodic table that's going to be applied in a variety of ways. Electron affinity. This is the energy change when a gaseous atom gains an electron to form a negative charge. So this is a neutral atom gaining an electron and becoming negative. The way this is defined, the technical definition, it means the atom has to be in the gas state. That's when it's measured. And IB is pretty particular. If you have to define this in an IB exam or an exam I give you in this class and you leave off gaseous, for instance, you would probably not get full points. So we need to be very careful with these definitions and not be sloppy in our thinking about the definitions. Something I'm not mentioning here is ionization energy. This was defined for you earlier. Ionization energy is sort of opposite. This is where we have an atom. It's again in the gas state, so we'll just call it M. If it loses an electron, see, I'm showing my neutral, it should also be a gas. I'm showing my neutral atom here losing an electron. That's called the ionization energy, which we've already talked about a little bit. So, kind of, sort of, ionization and electron energy are opposite. One of them is gaining an electron, that's electron affinity. Ionization energy is the energy it takes to remove an electron in the gas state. That's ionization energy. So, that's it for our introduction. Thanks for listening, folks, and we'll talk more about all these things in the future.